Thank you. Thank you for staying until the very end. It actually gives me great pleasure to introduce my own colleague here at the MagLab, Steve Keel. Steve actually was educated at Cambridge and came to the US for a postdoc. And I think, according to your CV, you started in BU and then came down to the MagLab for a postdoc. How did that happen?
Oh, that's correct. You made a horrible mistake there. I was actually dark blue, not light blue. I was in Oxford, not Cambridge.
Oh gosh, okay. I hope it doesn't trigger any war or something. Anyway,
but,
okay. Anyways, thank you for the correction. Yes.
But Jim Brooks was at BU, and
that's what I thought.
he
Yes.
hired me at BU, and then we moved down together when the MagLab moved.
Okay. Well, in any case, you came to the MagLab first in Boston and then down to Tallahassee for your postdoc, and then Steve actually moved to Montana for a faculty position and found it wasn't hot enough there, so he moved back down to Florida, but landed in the wrong place, just like I did. Okay, I mixed up between Oxford and Cambridge, but he went to the wrong Florida University. That's University of Florida. And he corrected that mistake, unlike in what he did for me, which only lasted a few seconds. He made that mistake for, I don't know, 7-8 years. And he corrected that, I guess, 7-8 years later, and moved back to Tallahassee and the MagLab here and joined our faculty. In any case, so he is one of our 2 experimental speakers for the school, and he will tell us about spin dynamics. Okay, so go ahead, Steve. The room is yours.
So thank you very much, Kun. Actually, I still have great friends in Gainesville at the University of Florida and even at Montana. And some of the work I'll present today actually is a collaboration that involves a number of folks at the University of Florida. So those of you who don't know, the Magnet Lab is sort of distributed among 3 different sites, one being at Los Alamos and then the other one at University of Florida, and then the headquarters is here. So we have very good connections with the University of Florida. So this talk will be a little bit different, I think. I was not able to follow the other experimental talk, but I've seen these wonderful tutorial-like presentations with, literally writing out the notes in real time. And I apologize in advance that my talk is not going to be like that. It's going to be presented more as a PowerPoint, but my hope is that it is tutorial-like in the sense that I'm going to be describing how we measure or observe spin dynamics using the technique of electron spin resonance. But to do that, I'm going to go through slowly a lot of the concepts that are relevant, including, and I apologize, there's a section here in the middle which might be familiar to quite a few people, describing the idea of a rotating frame and how you make a Hahn echo measurement to measure the coherence of an ensemble of spins. And it might be well known, but my experience has generally been that when I give talks on this, I generally find it's not such a well-known thing. So I will spend a little bit of time going through this. I'm going to begin, though, by discussing the main problem that we're trying to understand, and that is the idea of magnetic decoherence. And in fact, not just magnetic decoherence of spins, but other sources of decoherence as well. And I'll describe something called a spin clock transition, where we can provide some degree of protection against magnetic decoherence. It's not, decoherence free space, but it provides a degree of protection, and one can observe prolonged coherence in the kind of spin systems that we're interested in. And those systems that I work with are molecular systems, so I'll spend just a few slides talking about those materials and why they're interesting. And then hopefully, if I don't take too long on the introduction, I will present some very nice results illustrating all of the points that are in the introduction. I've written up here EMR because I shortened it in the title so it fit in 2 lines. EMR stands for electron magnetic resonance. It's kind of a loose term that we use to describe everything we do in the group that I lead here at the MagLab, which is a user program. Today, I'm going to talk primarily about electron spin resonance, but there are many other forms of resonance. And in the interest of sort of truth in advertising, I did join at the very beginning, and it was said that I was going to talk about spin pumping in antiferromagnets. And that is something, of course, we do. We do a lot of work with our users here in the user program, but I'm not going to say a word about that today. I decided instead to focus entirely on my own research, which is looking at the potential of using molecular materials as building blocks for future quantum technologies. So the main topic of this lecture today is really going to consider this fairly simple picture here, actually relatively simple, of a central qubit, which in my case is going to be an electron. It doesn't need to necessarily be one electron. It could be some coupled electrons in a transition metal or in a lanthanide ion. And it's surrounded, it's living in an insulating host, so there's no conductivity or free electrons around. But that host, embedded in that host are many other spins. So they may be other electron spins or they may be nuclear spins. So the red blobs here are supposed to represent protons and the blue blobs electrons. So I'm going to spend the beginning part of the talk discussing this model. And at some point also I'll talk about coupling to a thermal reservoir as well. But most of the talk will be about the magnetic part of this problem. So the system will be subjected to both obviously a static external magnetic field. It'd be a little bit strange if that was not the case, since we're based here at the National High Magnetic Field Lab. I'm also going to excite the central spin using microwaves. So when you do spin resonance, typically speaking, the frequencies are in the microwave range. So this conference is about non-equilibrium quantum systems. So you can imagine, in effect, I'm going to use the microwaves to excite the central spin. And then I'm going to look at how it talks when it's out of equilibrium, not far from equilibrium, but just excited away from its ground state, how it relaxes both in terms of quantum phase to the surrounding other spins, electron and nuclear spins, and also loses energy to the thermal reservoir. And in general, the experiments are going to be performed at relatively low temperatures. And of course, the important ingredient here is that I'm going to assume that there are dipolar interactions between all of the spins in my ensemble. So not only between the central spin and each surrounding spin, but also between the spins in the bath. And I will discuss some quantum simulations towards the end of the talk. So we do electron magnetic resonance, as I mentioned before. Really, for today's talk, it's just purely electron spin resonance. And of course, that is the language of quantum computing when you're dealing with spins. So if you're going to manipulate spins, electron spins, the way you do that is essentially through an electron spin resonance experiment. So you can imagine a two-level system, a spin 1/2. You can either represent it here in the Zeeman diagram or here in this block picture. By controlling the pulses of microwaves that you send to that spin, you can move it around in a controlled fashion, in a deterministic way, around this block sphere. So that allows me then to create the arbitrary superpositions of the up and down states that one might be interested in a quantum device. Now, of course, when the spin is away from its sort of basis states, it precesses in the magnetic field. And for a free electron, that precession frequency is about 28 gigahertz for every Tesla that you apply. And obviously that spin is precessing in the laboratory frame, but what we're going to do throughout much of this talk, and I'm going to come back to this later in more detail, but I just want to point it out right now, is that very often we analyze those dynamics from a frame that's rotating together with the spin. So this idea of a rotating spin description. So if you're rotating with the spin, and it's tipped away from the pole, so it's somewhere maybe, for example, in the equator, and you're in the rotating frame, then the spin essentially looks static to you. And so its quantum phase, the phase we describe here in the wave function, is constant within this rotating frame, if the rotating frame is rotating at the same frequency as the spin. And so now we can treat this problem in terms of, we can discuss the problem in terms of this block sphere description. So now go back to this picture of my central electron spin in a insulating host surrounded by other spins. And now what I'm going to do is I'm going to switch on the dipolar interaction. Initially, I'm just going to switch on the dipolar interaction between the central spin and the surrounding spins, but I'll also consider later on dipolar interactions between those. So in the absence, you know, simple Zeeman Hamiltonian here, in a magnetic field B0, this is a static applied magnetic field. This spin will precess at an angular frequency exactly equal to omega 0 until I switch on this dipolar interaction. So what you're going to see is that things will start to change when I switch on this dipolar interaction. So this representation of dipolar interaction here is not a very general one. It really just assumes that the two spins are collinear and they're joined by a vector that aligns with their z-axes, but it's mainly just to get the main point across. We can kind of divide the dipolar interaction into two parts. The first part, if you like, is the part that commutes with the Zeeman interaction, and then obviously there's an off-diagonal part here, which I'll discuss in a moment. And so, if the central spin is interacting with nearby electron spins, then this SC1, SC2 part of the dipolar interaction causes something that we call spectral diffusion. Because you can see what it sees, you know, it contains SC1, so it really just looks like it adds to the local magnetic field. And so it produces a small shift in the resonant frequency of this central spin. So it no longer now precesses at frequency omega 0, it will precess at a frequency that's slightly shifted away from omega 0. And so therefore it would dephase relative to the clock that I set running when I first put on my magnetic field. So there's some dephasing here that results from the SC interaction between the central spin and any surrounding electron spin. The other part of the interaction, which is a little bit harder, we're going to see in this talk, is a little bit harder to deal with. If I have, so this part of the interaction here, I can write it in terms of raising and lowering operators, and what it wants to do essentially is cause flip-flop type processes between two spins. But those processes are only really active when the two spins are precessing at the same frequency. So that's why we call this a resonant electron spin here. We're assuming that it's precessing at exactly the same frequency as the central qubit. And if that's the case, then these SXSY terms can cause these coflips. So not only do they change the phase, but they actually flip the orientation of the central spin. Now, I'm going to save discussion of these towards the end of the talk, but of course, if these flip-flop interactions act between two bath spins, what they do is they can change the polarization of say, a nearby spin that's not on resonance with the central spin. But what that will do is it will change the magnetic field, or the effective magnetic field, if you like, that's acting on the central spin. And so it will again cause changes in the resonant frequency of the central spin. So this spin bath has a lot of dynamics associated with it through these flip-flop processes. And they're rather hard to get rid of because they're energy conserving. So you can imagine if you have any electron spins, and I should generalize this, of course, to nuclear spins. The nuclear spins undergo the same dynamics, and at anything but, you know, even at very, very low temperatures, you're going to have nuclear spins that are polarized the wrong way, and those spins can mediate these flip-flop processes that propagate throughout the material. And they produce time-varying, very weak, but time-varying magnetic fields at the location of the central spin. And they act on the central spin through this SC type term. And therefore, they cause variations in the frequency and therefore in the phase of the central spin. And what we're going to, you know, the main point here is this is one of the main sources of decoherence in systems, in spin systems, where you have other magnetic stuff surrounding. And of course, you can always lower the temperature to get rid of other sources of decoherence, such as spin lattice relaxation. But it's very hard to get rid of this nuclear spin diffusion, which causes what we call spectral diffusion. Of course, there is a term that has SXIX and SYIY between the proton and the electron, but the frequencies associated with the dynamics of the electron and the nuclei are so different that you can, to all intents and purposes, completely ignore that. This noisy spin bath causes spectral diffusion, which ultimately is the source of decoherence in many spin systems at low temperatures. What I've argued here is that these mutual spin flip-flop processes, either involving pairs of off-resonant electron spins or off-resonant nuclear spins, modulate the spin dynamics of the central spin through the dipolar interaction, and it results in fluctuations of the frequency and of the quantum phase then in the rotating frame. So if you're in the rotating frame at angular frequency omega 0, if you change the frequency of your central spin, now it's going to wander away from you in the rotating frame. It's going to essentially dephase. I mentioned that this is mediated primarily by these flip-flop processes. Of course, it could also be mediated by T1 processes of the non-resonant spins. If this guy is facing the wrong way and it just relaxes, that's another source of decoherence. But it's mainly these energy-conserving nuclear and electronic flip-flops that are hard to suppress, and that's going to be the main focus of this talk. And so, I started out with this picture with this very sharp frequency omega 0, but in fact, for a central spin surrounded by all of these other spins, the frequency is not well defined. It wanders all over the place, and this is what we mean by spectral diffusion. The frequency of that spin wobbles around due to the dipolar interaction with the surrounding spins. So I've got just a little bit of a primer here to show what I mean by spectral diffusion. So supposing we have a two-level system, again, just a system of spin 1/2 electrons, and I can excite them to the excited state with, for example, a microwave pulse. Now, very often, as is very often the case in real materials, when you consider an ensemble of electron spins, the frequency spectrum of the ensemble is not single value, because there may be strains in the lattice that mean that one central electron spin might have a different frequency from other electron spins. And so you can imagine some static distribution of the frequencies of all of the spins that you have in your solid. And I've just represented it here as a Gaussian distribution. But one of the things that you can do in a time domain or pulse DPR experiment is that you could saturate the spin system at a very well-defined frequency, omega 0. So imagine now what I do is I drive the system at a frequency exactly or as near as possible to this frequency, omega 0. And if I drive it for a long time with a very, very pure frequency, what I will eventually do is I'll drive the spin system at that frequency to what looks like an infinite temperature. So I have equal populations in the excited and ground state. And at that point, the rate of absorption and stimulated emission, they're equal. And so you no longer have any absorption at that frequency. And so we say what you do is you burn a hole in the population of spins exactly at frequency omega 0. And if you didn't have this, so you can burn a very, very sharp hole if you do this with a very, very well-defined microwave frequency. But what you can then do is you can come back and you can image that hole. So you can do a subsequent time-resolved experiment where you image this entire profile at later times. And what you find is, due to the spectral diffusion, the central spins talking to the environment and their frequencies wandering off from omega 0 in both directions, is that hole sort of fills itself in and becomes broader and broader over time. Now, there will be some maximum width which it can broaden to, which is sort of limited by the dipolar interaction scale with the surrounding spins in the central spin. But that shows you here that rather than a very, very sharp frequency omega 0, you have this spectral diffusion. And that's really what you're watching here, is you're watching a dephasing or a decoherence process in real time. I'm not going to show you experiments like these, but I'll show you the decoherence in other ways later on in the talk. Now, there's no energy relaxation here. This is purely energy conserving processes. So the spin bath spins are just undergoing these flip-flop processes and just reshuffling the frequencies of the electrons in my distribution. So I end up with a much broader profile than I had to begin with. Now, there are, of course, many other sources of decoherence that are not going to be so important in my talk today, but I just wanted to point them out briefly. You can imagine vibrations that couple elastically to the gyromagnetic ratio, so that whenever you have spin-orbit coupling, this gyromagnetic ratio gamma that determines that frequency will be different from 28 gigahertz per Tesla. And if you have any dynamics associated with the underlying structure that couples to this, that can also cause decoherence. And there could be instrumental effects as well. You might have, for example, just static fluctuations in your applied magnetic field. But there is another problem, something called instantaneous diffusion, and that is when you try to excite your central spin, you may flip a nearby resonance spin as well. And depending on when that happens in your experiment, it may affect the dynamics of the central spin in an uncontrollable way. So there are many things that we have to worry about that can cause decoherence in a real experiment. And then finally, longitudinal relaxation. Of course, this is energy relaxation, where the spin relaxes back from its out of equilibrium position back towards its ground state. And that would obviously involve the loss of energy to the surrounding bath. And that ultimately limits the decoherence time T2. It's always going to be less than T1. And the main source of this energy relaxation in solids is the spin-phonon interaction. And that's why experiments are typically carried out at low temperatures, because you want to just get rid of as many phonons or vibrations as you can, so you don't have to worry about that problem, and then you're just left over with the magnetic one. But this direct flip-flop process, where the central spin undergoes a flip-flop with a nearby resonance spin, that also causes longitudinal relaxation of the central spin. It's not spin lattice relaxation, but it will completely relax the central spin and result in total loss of phase, and therefore it effectively limits T2. And that's a problem that's hard to deal with, as you'll see when I get later on in the talk. So the key point that I want to end this part of the presentation in is this idea of a clock transition. So everything that I've shown you up to now assumed a linear Zeeman Hamiltonian. So you have a linear relationship between the energy of the eigenstates and the magnetic field. But imagine that you have some off-diagonal term that doesn't commute with the Zeeman Hamiltonian. And there's many ways in solids that you can invent such a term, so that you have an avoided level crossing between the 0 and 1 states. If I now look at the transition frequency between these two states as a function of magnetic field, instead of being linear in magnetic field, it goes through a minimum, so it never actually gets to 0. So in 0 magnetic field, you actually still have a gap. So it's linear in high magnetic fields, but it's quadratic in low magnetic fields. And so we can think of this transition frequency, which is the frequency I need to drive transitions between the eigenstates of my central spin. I can think of it as a clock frequency, because it's really just telling me the rate at which my central spin is processing. And there's an interesting point here right down at the minimum, where the change, the dependence of the clock frequency on the magnetic field, but in other words, the derivative goes to 0. And the important thing here is, as you'll see later on in the talk, is that you also find that the expectation value of SZ of the central spin also goes to 0 at this point. And some of you might already recognize why that's important. So if you do, if you operate your central qubit, your spin, your qubit at this magic point, which we call a clock transition, you find that many of the sources of magnetic decoherence should go away, because they couple mainly through the expectation of SC of the central spin. So, for example, any instrumental noise, if the qubit clock frequency is completely independent of SC, then any noise on the magnetic field isn't going to couple to the spin. And the same is true with all of these flip-flop processes associated with the surrounding spins. They also couple to the central spin through SC1. And so one might expect coupling to the central spin through all of these processes will go away if you operate your qubit at this magic operating point that we call the clock transition. The only thing, unfortunately, you can't protect against are these flip-flop processes. So if you have a nearby spin that's on resonant with your central spin, that can still cause decoherence. But one can imagine ways that you might be able to, at least in some eventual device involving multiple qubits, you can actually think of ways that you might be able to engineer this process out of the problem by just having your qubits operate at different frequencies and only be resonant when you want them to. So in an eventual device, you could imagine ways to get rid of this. And then all of these other processes will go away if you operate them at a clock transition. And of course, this idea of a clock transition, it goes back to atomic clocks. I mean, this is the basic principle through which atomic clocks have their very high phase stability and therefore very high temporal stability, which gives them, makes them excellent candidates for time standards. And so you're going to see when I go into the experimental part of this tutorial that this is what I'm going to talk about: operating molecular spins at clock transitions and how the coherence is enhanced in doing so. So what systems do we study? My interest really since the early part of my career has been at the interface between physics and chemistry and trying to engineer things from the bottom up. When I started out 20 years ago, this was really a pipe dream, more than 20 years ago, but it's becoming closer and closer to reality these days. And so what we mean by a molecular spin system for quantum computation, actually these figures are taken from a recent Perspective article that we published. But what we mean by molecular spin qubits is essentially some kind of molecule that has within it unpaired electrons. And most of the time, these are associated with something like a transition metal. So all of these examples in the top here involve transition metals. And in fact, they're all spin 1/2. They don't have to be. There are many examples where you might have spin states greater than 1/2. But all of these examples here with spin 1/2, they've been studied. You can go back to about 2007, where the first people started to talk about using magnetic molecules for quantum information processing. And over the years, chemists have figured out better and better molecules that might be suitable for this task with quite good coherence. You can see in this case here up to 700 microseconds of coherence time, so almost a millisecond. Now, the work in my group has focused in recent years more and more on lanthanides. That doesn't mean that we don't look at transition metal systems, but we tended to focus on lanthanides. And so there's some examples of molecules here that we've studied. I'm not going to go into any detail on really most of them except this one on the left. And if there's time at the end, this one on the right. I'll explain on the next couple of slides why I find lanthanides kind of an interesting route to go. Actually, one of the motivations is the fact that the ion trap community have been working with lanthanides for many years. So we're sort of working along this line of trying to use molecules to trap lanthanide ions in the same way that the ion trap community do and generate quantum hardware that way. So in this case here, you have a very large spin orbital moment. So you not only do you have a large number of unpaired electrons on the holmium ion, but you have a strong orbital contribution to the moment as well. The interesting thing is here over on the right, the last system that I'm going to consider, we actually get back to the situation where we're just considering a single unpaired electron spin associated with a lutetium ion. Now, why does this problem, why does this area fascinate me? Lanthanides in some way, because of their contraction, the lanthanide contraction, the magnetic electrons are well screened from their environment, and their electronic properties are essentially atomic properties. They're not modulated very significantly by whatever you attach to their periphery. So you can more or less predict what the electronic density looks like of a given lanthanide ion in a given molecule. In other words, I could take a given element and put it in a range of different molecules, and the electronic density doesn't change a great deal. Now I take the molecular part where I attach the lanthanide ion or embed it within this organic part, And it's this organic part that allows me to control the interaction with the charge density on the lanthanide and the charge on the surrounding organic part, which we call a ligand. So this orbital shape and how many electrons we put into the f orbital, and then how, like with Lego, I build it together with a molecule, more or less allows me in a very predictable way to basically build a Hamiltonian with the properties that a spin Hamiltonian with the properties built into it that I'm looking for. And so chemists have gotten to a point where they really understand this very, very well. So you can more or less predict that if I take this ligand and a given lanthanide, that I should have an electronic state that has the properties that I'm looking for. And that's what really. Yeah.
So, sorry, I have a question. Maybe I interrupted you. But what was the guiding principle for how you came up with all the structures? Like, was it based off, like, was it just chemical intuition of some sort, or is there like some quantum chemical calculations, or what was for all the structures that you showed us? What was the guiding principle, if I may ask? Or
I couldn't go into every single one because each one would almost be a talk. I hope that as I go through this talk, this one and this one will become clear. I may not get to this one in time, but we'll see.
Okay.
So the point is, what I want, I want a spin Hamiltonian that's going to have a term in it that's going to give me one of these clock transitions. Okay. So this molecule here has a very, very high symmetry. It has these fourfold phthalocyanine ligands. They're exactly fourfold symmetric, sitting above and below the lanthanide ion that sits in sort of trapped in between. And it turns out that this angle is almost perfectly 45 degrees when you crystallize these things. And so in that case where the one above and the one below are exactly eclipsed at 45 degrees to each other, the symmetry, the point group symmetry of the lanthanide, it doesn't matter which lanthanide it is, but the local point group symmetry is D4D. Now that's not one of the exact crystallographic point groups, but it's very, very, but you get very close to this symmetry in the solid state. And it just so happens that because of the time reversal invariance of the spin-orbit interaction, it means that your spin, when you apply a magnetic field, or rather the spin Hamiltonian will always can have a higher symmetry than your crystallographic symmetry. And so you kind of lose a depth perception. So this molecule here, where if I color code the one behind in the light gray and the one above in dark gray, you can see which one's behind and which one's in front. But if I lose that depth perception, it actually looks like it has an 8-fold symmetry. And it turns out you can't specify any off-diagonal. So if you imagine writing down a spin Hamiltonian for some lanthanide ion sandwiched between these two molecules, it's a very axial environment. So you can have operators like SC squared, SC to the 4th, SC to the 6th. You never go beyond SC to the 6th for a lanthanide. If you want to then specify a transverse anisotropy that reflects this apparent 8-fold symmetry, you can't do that with 6-fold operators. You'd have to go to 8th order. And so it's a little bit like, so it essentially has a perfectly cylindrical symmetry. And so therefore, SC would be an exact quantum number. So you would imagine then that you have a spectrum, a little bit like I show on this next slide here. So for exact D4D symmetry, it doesn't matter what I put in here, I should have a perfectly linear Zeeman effect. So even though it might be a spin orbital moment, it's not a spin 1/2. It sort of looks like almost like it obeys Cramer's theorem. There's no degeneracy here. So there's a degeneracy, there's no symmetry breaking here. So what I really want to do is I want to then twist this thing so I break that D4D symmetry and have something more like a C4 symmetry. And now I can open a gap here, which gives me an avoided crossing. And so the chemists, they know how to do this. So for example, here's an example of a family of compounds where you coordinate a lanthanide ion with these thioacetate groups. So there are 8 of them as you go around the molecule. And depending on what you put on as a counter ion, you can change the angle. You can change the angle between the coordination from above and below from 45 degrees, where you have this exact D4D point group symmetry, to something different from 45 degrees, where you have a C4 symmetry. And so all of these ideas, they're well known, and the chemists understand them. So we as physicists can talk to the chemists and say, look, if you give me a holmium ion in this coordination and you twist it, I can get exactly this Hamiltonian that I want, that has the properties that I'm interested in terms of generating a clock transition. So it's not luck, it's not, and that's the beauty of molecular chemistry. You really have this immense control at a microscopic level of the underlying spin Hamiltonian. And then of course you can functionalize that so that these things can, for example, be attached to a surface or attached to each other, and so on and so forth. So there's a really tremendous chemical control that you have. So that's the basic idea here. So if I choose a given molecule with a given coordination and I get the angle that I want, I can generate a clock transition. And if I can tune that clock transition into a frequency range where I can do pulse DSR studies, I should be able to now study the coherence of this thing exactly at one of these clock transitions. So how do we study them? So this is the next part. I'm already over 30 minutes, so I'll probably go through this reasonably quickly. I found out I can stop this. Various points. So let me first go back to this rotating frame idea. So let's go back to the beginning of the animation. Oh, sorry. Go back. Pause this here. So when you apply a static magnetic field, this worked when I was not in presentation mode, and it doesn't work when I am in presentation mode. So I'm just going to have to let the thing run. So let's see if I can stop it at the right part when it comes around again. So we start with a static magnetic field, and the red arrow, so the blue arrow represents the static magnetic field, and the red arrow represents the spin, which is now going to process around the static magnetic field. And at some point when this arrow goes along here, it's going to transform to the rotating frame. So let me just let that run. So see, now you're rotating with the spin. So now, as far as you're concerned, the spin looks like it's static in your frame and the lab is spinning around you. Now what you can do is you can apply an oscillating electromagnetic field transverse to the static magnetic field. And that is how that you would then cause your electron spin to change its orientation on the Bloch sphere. So of course this requires that the electromagnetic field is, or the oscillating magnetic field is transverse to the applied field. So the idea here is you apply, in addition to your B0, which is the static magnetic field, you apply a microwave magnetic field that has a frequency which is the same that your electron spin is rotating, but it has a circular polarization, so it rotates together with a rotating frame. And so now that microwave field actually looks static within the rotating frame, and as a consequence, the electron spin in that rotating frame can now just rotate about the static magnetic field. So if I then put my microwave pulse on with my oscillating magnetic field for a fixed amount of time, I can rotate my spin more or less anywhere I want over the Bloch sphere. So that's how I can achieve this in experiments. I send pulses of microwave at the same frequency that the electron spins are processing onto my sample. And by controlling the length of the pulse, I can determine over what angle they rotate on the Bloch sphere. Now you might say, I need circular polarization. Of course, that's not that difficult to generate, but it turns out that even with linear polarization, it works, because you can think of linear polarization as two counter-rotating, a superposition of two counter-rotating circular polarization. So one of those polarizations can do the job, and the other one sort of goes along for the ride. And then the other thing is, if I vary the phase of my microwave pulse, in the rotating frame, that dictates whether my microwave V1 field is going to be along X, along Y, or any angle in between. So by controlling the phase, I can achieve rotations either about the X-axis, the Y-axis, or more or less any angle I want. So not only am I controlling the angle theta over the Bloch sphere, I can control the phase on the Bloch sphere as well. So this is how we implement, if you like, quantum logic with a spin using microwave pulses. This Bloch sphere representation, this rotating frame representation. So all we need then is to control the length of the pulses to determine how far we rotate in theta, and then the phase determines which plane that we would rotate in. And then what we do to measure coherence is we perform something called a Hahn echo. And so again, this is going to take a little bit of explanation, but I'm going to go through it in several steps. I'll start with this animation, but I'm going to break it apart into different steps within the animation. So the first thing to say is that in my lab, we don't study single electron spins. The sensitivity of the techniques that we use in my lab are not capable of detecting a single electron spin. So we study ensembles. We take a crystal that has many of these spins, and some of them are going to be resonant with our microwaves, many others will not. All the ones that are resonant, we can consider those to be central spins. And so we perform these series of echoes, perform these series of microwave pulses. And at the end, we generate something called an echo. So I want to try to explain now step by step how this happens. So I've broken the movie down into individual steps here. So over here, we can consider that my ensemble, of course, there are going to be some spins that are up and some are down, but I've got a magnetic field on, so I have a net number of spins that are up as opposed to down. So I have a net magnetization that points along Z. And so the first pulse that I apply is what we call a 90-degree pulse, or a pi/2 pulse. So I just put my microwaves on for exactly enough duration that the magnetization processes into the XY plane. I can either do it with an intense pulse for a short amount of time, or a long pulse for a short amount of time. So for a long amount of time with a low microwave V1 field. But I know how to control the angle in my spectrometer. So I tip those spins into the XY plane. Now, because of the finite bandwidth of the pulse, so I'm doing a pulsed experiment here, so that my microwave pulse has a finite duration in time, so it has to have a finite duration in finite bandwidth in the frequency domain. So I'm going to excite spins in my ensemble that actually have different precession frequencies over some bandwidth. Either it's going to be dictated by the bandwidth of my first pulse, or by just the width of my EPR spectrum to begin with. So I'm bound to have spins that have frequencies that are bigger than omega 0, and I'm going to have some spins that are slower than omega 0. So as I let the system evolve between this first 90-degree pulse and the next pulse that I'm going to apply, in the rotating frame, some spins are going to go faster, so they're going to move out in front of my y-axis, in this case, in the rotating frame. Other spins are going to move more slowly, going to precess more slowly, so they're going to fan out backwards in the rotating frame. And so in some sense, this is a form of decoherence in the sense that different spins have different frequencies, and so they dephase from each other over time. So the magnetization spreads out over the Bloch sphere over time. But what I then do is I apply a 180-degree pulse, and that takes that entire fanned out magnetization and just flips it over 180 degrees in the rotating frame. And this pulse is effectively the same as a time reversal operation, because what it did is it took all of the spins that were leading and it moved them to the back of the bunch, and all of the spins that were lagging and moved them to the front of the bunch. And as a result, this dephasing that occurred due to the fact that the spins have slightly different intrinsic Larmor precession frequencies, they will then start to refocus. And at some later time, exactly equal to the same amount of time between the first pulse and the second pulse, they come into focus again. So they form a very sharp, well-defined magnetization in the XY plane. Now, of course, whenever spins are out of equilibrium, they're always going to emit microwave just through spontaneous emission. So a rotating magnetization will always lead to a very weak emission of a microwave signal. When the spins are very, very spread out, they're not in phase with each other, the microwave signal that's emitted is completely incoherent and you won't detect it. But when the spins are back in phase with each other, so when they come back in phase, you get a burst of microwave radiation exactly in phase with the original excitation. And so you get back in your spectrometer an echo. And the only problem is this echo is orders of magnitude in intensity below the intensity of the pulse that you use to excite the spins in the first place. There's a nice analogy that you'll find on Physics Today. I think it's from the 60s or somewhere like that. But you think about it as a race, and you fire the starting gun, and all the runners run off. But of course, some of them are fast, some of them are slow. And so over time, they spread out. Now imagine at some later time, you fire the gun again, and that instructs them to run back to the starting line. If the speeds of the runners were just intrinsic, in other words, they ran at a constant speed on the way out and a constant speed on the way back, it's just that some of them were fast and some were slow, then they should all come back in perfect phase when they get back to the finishing line. And so in principle, this spin echo, in the absence of any dynamic fluctuation, so that the reason why the spin spread out here is just because of static disorder. The fact that different spins are in different environments, so they just have a slightly different Larmor precession frequency. So if there's no dynamic effect, then the spins will always come back perfectly in focus, and you'll nicely see this spin echo. If, on the other hand, you have some dynamic disorder or dynamic fluctuations, or, for example, in the case of the runners, imagine that as the runners run out, some of them get tired more quickly than the ones than others. So their speed is not a constant on the way out and on the way back. Then they won't come back in phase when they come back to the starting line. There'll be still some spread. And so you can think of this tiredness as decoherence. And in the language of spins, of course, that would be due to effective fluctuating local magnetic fields due to the surrounding environment. Now, if you vary the time between these pulses and the echo, as it gets longer and longer, these dephasing processes will have a bigger and bigger impact. And so the refocusing where you see this echo will get worse and worse with time. So what you do is you do this sequence with a fixed time, and then you start to vary this time between the pulses and the echo. And at longer and longer times, the echo that you get back gets weaker and weaker and weaker because of temporal dephasing. So in other words, things that you can't refocus. So you can always refocus static disorder, but you can't refocus temporal fluctuations in the phases of the spins. So that's how we're actually going to go about measuring the coherence of electron spins using an ESR spectrometer through these control pulses and measuring back these echoes at later times, and then measuring the strength of an echo over time to determine the coherence time. Now, this is not my work. This is actually work of Andres Heinrich, who's in Seoul at Ewell Women's University. But it turns out you can nowadays do measurements on single spins. I felt it was important to point this out. It's not easy. There's very few groups in the world that can do it. But with an STM, you can imagine positioning your STM over a single atom on a surface that has an unpaired electron spin. And by applying an RF field to your tip, you can actually manipulate that spin. And you can even read out the spin by looking at the tunneling current through the spin from the tip into the substrate. And if you put a spin polarized, if you have a pinned magnetic defect on the surface of your STM, the current that flows here is spin polarized, so it can actually detect the difference for when your surface spin is pointing one way or pointing the other way, in other words, parallel or anti-parallel to the tip spin. Now, of course, when you do a quantum measurement on a single spin, you can only ever measure it in the two basis states, either up or down, and not in between. But effectively, these measurements, the signal to noise is not great, so you do a lot of averaging. And so after you've done the averaging, it's almost the same as performing an ensemble average. So, for example, you can do exactly the same thing, where you perform a Hahn echo sequence and you look at how that Hahn echo then decays over time. And so you can measure a coherence time associated with with a single spin. But you have to have some device that can read out a single spin in order to do that. And you can't do that with a conventional ESR spectrometer. You have to have some kind of nano, something with atomic scale resolution like an STM. So here are examples of echo decay, where you measure a coherence time and Rabi oscillations that are performed on a single titanium spin on a surface using this setup. And these are pretty recent results, and this field is still, I would say, somewhat in its infancy, but it's making enormous strides. In our lab, we do this with a range of spectrometers, and I just show you one instrument here. Of course, because we're at the MagLab, we do things sort of differently from everybody else. Most ESR spectrometers operate at a fairly low frequency of about 9 gigahertz. We have a range of spectrometers that allow us to do pulsed ESR experiments all the way from 9 gigahertz up to 90 gigahertz. This one operates at about 94 gigahertz, all the way up to several hundred gigahertz. So it allows us to do these coherent spectroscopy, coherent pulsed ESR measurements over a very wide range of fields and frequencies. I really don't, in the interest of time, have the time to go into detail about how this spectrometer works. So I think I'm going to move on to the experimental results. But I just want to mention that to generate these high frequencies, we still use completely solid state electronics. So we do all the frequency programming at a fairly low frequency, the sort of same frequencies where our cell phones operate. We can even build in some arbitrary waveform capability, so we can really program these waveforms quite precisely. And then we multiply them up to the frequency where the spectrometer is going to operate, and then amplify them. And we amplify them up to somewhere like a kilowatt of instantaneous power, because it turns out the magnetic interaction between the B1 field, the field in the microwave, is in order to get it up to the strength where you can rotate spins on nanosecond timescales, you need kilowatt powers. And then we propagate everything optically. But this allows us then to control spins very precisely at these high frequencies with quite well-controlled pulses with nanosecond time resolution. So let's go on to some results. So this relates back to Hitesh's question. So this is a molecule that we were interested in. We've been studying for many years, in fact. And it's full of surprises. So again, it has this interesting coordination of 4 oxygen atoms above and 4 oxygen atoms below. So it looks like it has this D4D coordination environment. But this angle is slightly different from 45 degrees, which turns out to be important. Now, holmium has a 10 unpaired F electrons, actually not 10 unpaired, it has 10 F electrons. Some of them pair, some of them don't. You end up with an orbital moment of L equals 6, a spin moment of L equal 2, and they couple through spin orbit coupling to give you this rigid J equal 8 spin orbital moment. And it turns out that when you then insert this holmium ion into the molecule, it causes a very large crystal field splitting of the different plus or minus MJ states. So you can imagine plus or minus MJ, plus or minus 8, 7, 6, 5, 4, 3, and so on. And the exact details of this crystal field results in the fact that at lowest energy, you just have the plus or minus 4 state. So all of the other crystal field states are much, much higher in energy. So at low temperatures, we can completely neglect them. So it really is electronically just a 2-level system. It's not a spin 1/2, but it's a plus MJ4 and a minus MJ4. So it's just 2 electronic states. But because of the 4-fold symmetry of the molecule, there's a crystal field operator that breaks the axial symmetry and is very effective in mixing MJ plus 4 and minus 4. And so what it does is it produces this very large avoided crossing between the MJ plus or minus 4 states. Now, this diagram, of course, looks much more complicated than one that I showed you earlier, where I just had 2 levels and an avoided crossing between them. There's an added slight complication in that the nuclear spin of holmium is 7/2. It's 100% abundant, and it couples quite strongly through a hyperfine interaction with the electronics moment. And so each of the plus 4 level and the minus 4 level, they split into 8 states that just correspond to the different projections of the nuclear moment. So from minus 7/2 to plus 7/2. So there are 8 levels down here and 8 levels down there, up there. But in an ESR experiment, you're flipping electron spins, not nuclear spins. So there's a selection rule that means that you always do a transition from the same nuclear projection to the same nuclear projection. So you actually end up with 4 avoided crossings here. In fact, there are 8 because there are another 4 on the negative side of zero field. So there are 4 clock transitions here and 4 clock transitions on the other side of zero magnetic field. And each clock transition just corresponds to a different nuclear spin projection. And if you look at the transition frequency, as you approach the clock transition, for each one of these clock transitions, it just goes like a parabola. So it goes through a minimum. And so here I would expect a transition frequency that doesn't depend on the electromagnetic field. And so I'd have a clock transition here, a clock transition here, and so on. So I'd have 4 clock transitions. So just a slight added complication with this particular molecule. If it had a nuclear spin of a half, then there would just be 1 clock transition. Don't worry too much about this broadening here. It just has to do, it's for a different talk, but effectively there's some inhomogeneous broadening in the system. So these levels are broadened quite a bit vertically, but not horizontally. So even though there are molecules with different clock transition frequencies, the magnetic field where the clock transition occurs is very, very well defined. So I can just park at one of these magnetic fields and do a spin resonance experiment there, and I ought to find enhanced coherence. And so here is the sort of the key result, but I've got some much nicer results coming in a minute. So the first sort of, if you do a very coarse grain measurement of the T2 time, as you measure by one of these Hahn echo experiments, as you sweep the magnetic field either side of each of these minima. So this is at 23.5 Tesla, which is right where that minimum occurs. This is at 70.9 millitesla, and 118 millitesla, 165 millitesla. So I just tune a few millitesla either side, you can see this very precipitous drop in the coherence time. So it's a very sharp divergence of the coherence time at each of these minima. So it's sort of confirming what I predicted about the fact you would have enhanced coherence of these clock transitions. I'm going to now zoom in much more closely on this first one. It turns out the divergence is sharpest. It gets less divergent as you go to higher fields. And again, that has to do with disorder associated with the crystals of these things. It turns out there's a little bit of twinning, and so there's a little bit of orientational disorder, and so that does cause some horizontal smearing of the clock transition, and it's more pronounced at higher fields than is at low fields. So this is by far the sharpest clock transition. And these are some absolutely spectacular measurements that were done by a former graduate student of mine. So it's the same measurement you saw on the previous slide, but what we're doing now is we're detuning from the clock transition by fractions of millitesla. And so we're looking at how the T2 varies. I know it says T1 here. I'll explain in a moment why, but there's T2. That's what we're plotting on these graphs. That's a function of detuning away from the clock transition at 23.5 millitesla. And a detail that I didn't mention earlier, but of course you can make these, another beauty of lanthanides is you can make the non-magnetic analog, in this case yttrium, so that you have a completely non-magnetic host, and then you can dope in certain percentages of the holmium so that the holmiums are quite well separated, which is important, if you want to really understand these magnetic decoherence processes. So these 2 samples here are at 1% concentration and 0.1% concentration. So 1 in 100 sites is holmium, or 1 in 1,000 sites is holmium. And you see this beautiful scaling as you approach the clock transition. So if I plot it on a log-log plot, you see I have a beautiful straight line. So this region where there's a curve here, I have perfect power law behavior of the coherence time as a function of detuning from the clock transition. So that tells me that the dephasing rate really is dependent on, if you like, not the curvature, but the slope of these curves here. So right at the minimum. So since the frequency depends parabolically on the magnetic field, when I take a derivative, I would expect the FDB to be linear in magnetic field. And so that doesn't necessarily mean that the relaxation time depends linearly on the magnetic field, but it might depend on some power law fashion on the detuning from the clock transition. I get different exponents for the 2 concentrations. So it seems that when I go away from the clock transition, it does matter what my holmium spin concentration is. So as I tune away from the clock transition, the exponent does depend on the concentration. And that exponent is something we haven't quite resolved yet. That's exactly what controls that exponent. But obviously, as I have more holmium spins surrounding, so I have a higher density of holmium spins, the drop-off of T2 is faster than it is as I have fewer holmium spins. But right at the clock transition, the T2 is completely independent of concentration. So it's about 7 or 8, somewhere between 7 or 8 microseconds. So it doesn't matter whether I have 1% holmium or 0.1% holmium. So the concentration, in other words, how you know, the proximity of other holmium spins, I'm completely insensitive to that at the clock zone transition, which is telling me right away that the spins that I'm exciting don't seem to care about the amount of other holmium spins that I have surrounding. So it does look, to first intents and purposes, like I've protected my central spin from all of the other holmium spins at the clock transition. So it looks like I've succeeded in achieving what I set out to achieve. Obviously, it's being limited by something else. So if it was purely magnetic decoherence, we'd expect this power law to just carry on all the way right up to the clock transitions. You just continue to diverge. But something else is limiting it, and we believe it's the longitudinal relaxation, the spin lattice relaxation, T1, because we've measured that independently, and it's about 10 microseconds for these samples at the temperature where these experiments were performed, which is actually relatively high temperature. It's 5 Kelvin. So what's happening is T2 is just running into T1, and T1's shutting off the T2 process. And that's not surprising in a lanthanide where you have strong spin-orbit coupling. Strong spin-orbit coupling means you'll have strong spin lattice coupling. So unfortunately, the T1s are quite short for lanthanides. And so, you know, that might ultimately be a problem because it might ultimately tell us what the shortest T2s, sorry, the longest T2s that we can achieve in these systems, because they're limited by the spin lattice relaxation time. Now, I don't show the data here, but it turns out if you go another order of magnitude in concentration, so you go to 10%, where you've got 1 in 10 holmiums, the maximum T2 really does start to drop. So it does seem that it depends on concentration as you go to much higher, concentrations. And so we think what's happening there is that once you have a high enough concentration, these direct flip-flop processes between holmium spins start to kick in, and they limit the coherence at the clock transition. But at least at low concentrations, when the spins are relatively far apart, these direct flip-flop processes don't seem to matter because there's no difference in the maximum T2 here or here. So even more interesting now, these curves on the right here are actually the echo decay curves that we measure. So I showed you how we do a Hahn echo measurement. So I showed you that, you know, we do pi by 2 pi, and then we get an echo, and then we just extend the delay time between the pulses, and you would expect the echo to decay. And so these are actually the raw data that went into producing these curves. And, you know, I can't fail to notice here that there is this really strong oscillations on the echo decay curves. And this is an effect that's well known. It's called ESEAM, electron spin echo envelope modulation. This measurement here was done on the top sample here, the 0.1, the x equals 0.001 or 0.1% sample. And the measurements you see on the right were done where the arrows are in the figure here. So what it turns out what these things are, they're actually coherent coupling that occurs during the early part of the decay of the coherence of your central spins. It's coherent coupling to surrounding nuclear spins. In fact, in this case, we can show that they're protons. Even though there are no protons in this formula here, there's a lot of other stuff that sits on the periphery of this molecule. There's a lot of water of crystallization. So there are a ton of protons in the lattice of this compound. And the electrons see those protons, and I'll try to explain in a moment what the origin of this oscillation is, the coherent coupling that gives rise to this oscillation. So you're actually seeing coherent electron nuclear spin dynamics here in the initial part of the decay. But what's remarkable, of course, is right at the clock transition. So we're sitting at the peak here. The decay is perfectly exponential, and there are no oscillations. So it looks like whatever this coupling between the electron spins and the surrounding nuclei, it goes away when you're at the clock transition and you have the slowest decay. But as you move away from the clock transition, this coherent coupling grows in amplitude. So you can really visualize and see here how the holmium spins are coupling to nearby protons. Now, if you take a Fourier transform of each of these decay curves, you get a spectrum with quite a few frequencies. It's a little bit noisy, but there's no fudging here. This is what the raw Fourier transforms look like. You see a peak that moves. So basically, the bottom one here is the Fourier transform of this one, and the top is the Fourier transform of this one. So you're moving up in magnetic field through the clock transition. And so the center frequency of these, so there's a peak here that's split, but its center frequency seems to move up in frequency. So I'm plotting the red peak here and the green peak here. Sorry, the green peak here. There are two peaks here, but the average of those two frequencies is this dashed line. And there's also a higher harmonic that emerges here, but it's just a single peak. And I plot that here. And it's no coincidence that for the magnetic fields where these measurements were done, the dashed red line and the dashed blue line exactly correspond to the Larmor precession frequencies of protons. Now protons are completely isotropic, so it doesn't matter where they are in the lattice. You put a magnetic field on, they precess at a very, very well-defined frequency that you can just look up in a book. So it's screaming at us right away that this effect has to be the holmium coupling to protons. And it turns out, I'll go through briefly through the theory in a moment, and I can see I'm getting towards my time, that the splitting that you observe between the two peaks here is actually a measure of the hyperfine coupling between the protons and the holmium. So it's the proton Larmor frequency that sort of sets the scale of the frequencies at where you see these modulations. But there's an additional splitting within the lowest fundamental harmonic, and that splitting is a measure of the hyperfine coupling between the protons and the holmium spin. And you can do them sort of back and envelope math. I'm not going to do it here, but you can work out it really just corresponds to dipolar coupling between the holmium and the surrounding protons. So it's not a contact interaction, it's purely through space dipolar interaction. I see I'm getting low on time, but what I want to just get through here is that the origin of this eSeam effect, this so-called electron spin echo modulation, these oscillations that we observe on the Hahn echo decay curves, it comes from the fact that you always have non-secular terms in the hyperfine interaction between the electron spin and the nuclear spins. When I gave the hyperfine interaction earlier in the talk, I made this simplification that they're collinear and they're connected by a line that joins the z-axes. But in reality, if you really compute the hyperfine interaction properly, there are a lot of terms that include, for example, SC of the electron with the IX of the proton. And so now, when you're trying to do an ESR experiment and flip electron spins, there are processes where you can also excite forbidden transitions, where you flip both an electron spin and a nuclear spin. So this diagram here, the red arrow represents the nucleus and the blue arrow the electron. So transition from here to here would be an electron transition, where you're flipping the blue arrow from down to up. Same here, down to up. An NMR transition would be where you flip the red arrow from up to down, So NMR transitions would be here. They're not shown on this diagram, but they're also allowed. Well, they're formally forbidden, but they are allowed. The dipolar interaction, these non-secular terms in the dipolar interaction, means that they're weakly allowed. And so you can actually do nuclear spin flips during your Hahn echo sequence. And this is what we call instantaneous diffusion. So maybe your pi pulse, you flip an electron spin, you look at it evolve, but then when you do the refocusing pulse, you flip a nuclear spin as well. And so you've changed the local magnetic field on your central spin. And so the way that it refocuses gets modulated by the fact that you flipped a nuclear spin during the course of the Hahn echo experiment. And that's why you can end up with these modulation effects. And the theory predicts exactly what we observe, that you should see harmonics at the nuclear Larmor frequency plus or minus half the hyperfine coupling, and also at twice the nuclear hyperfine frequency. You would also see a low frequency effect, but we can't measure down here because the Fourier transform doesn't produce any signal down at these low frequencies. So the effect that we observe is essentially a coherent dynamics associated with the electron and nuclear spins. But of course, these non-secular terms that result in the flipping of a nuclear spin together when you're flipping an electron spin, they depend on SC1. And what we've shown is that the clock transition, the expectation value of the SC of the electron spin goes to 0. In fact, it turns out all expectation of SC, SX, and SY, they all go to 0 at the clock transition. And so these forbidden transitions, or formerly forbidden transitions, become completely forbidden at the clock transition. And so you wouldn't expect to see any Eocene effect at the clock transition. So we sort of demonstrated both pen and paper and also experimentally that we completely decouple our Hamiltonian spin from the surrounding nuclear spins at the clock transition. So experimental talk. So I'll just spend a couple of slides talking about simulation. So we're not entirely experimentalists. We can deal with simple spin models, but I was sort of wanted to got to this point sort of be a little bit humorous. You know, our toy models tend to be rather simple, but the point is we can develop a model where we can actually capture a lot of what's observed in the experiment. Being experimentalists are not very adept at, you know, all the theoretical techniques that might be out there to solve a more realistic picture. We sort of try to reduce it to something that we do know how to solve, and we do it by exact diagonalization. So there's really no approximations. Now I mentioned this holmium is a J equal to 8, so it has a total angular momentum of 8. And so that would take up quite a few computational resources if we try to simulate a spin orbital moment of 8. So we reduce it to the simplest thing that can give us a clock transition, which is a spin 1. So it turns out you can't get a clock transition purely from a single spin 1/2. You could get it from a spin 1/2 coupled to another spin 1/2 or an I 1/2, but you can't get it purely for a spin 1/2. So you need at least spin 1 to generate. And it has to do with the fact that these crystal field terms that cause the avoided crossing, they're always even powers of the spin operators. So you can only really generate an avoided crossing, for example, between the plus and minus 1 states of a spin 1. So we treat a single spin 1 surrounded by 7 protons. Why 7? It's just sort of a compromise between the time of these calculations and, in other words, if you make them bigger, it just becomes unmanageably slow. So what we do is we take a single spin 1, we surround it by 7 protons that are sort of randomly oriented and randomly initialized. And also they're at random distances, although with an average that's typical of what we would find in the solid state. So that they're roughly in the proximity to the central spin that they would be in a real crystal, but they're not all at the same location, and they're not symmetrically distributed. We don't want to introduce sort of artifacts that way. Then we consider a hypokine coupling between a dipolar coupling between the central spin and all of the surrounding spins, and a J coupling. So it's actually an isotropic interaction, which might not be exactly right, but it captures the physics between the protons, and that's very important in this model, as you'll see.
Do you optimize? Sorry for the question. Do you optimize your parameters to match the experiment or something?
No. This work is actually currently in the archive, and it's under review. And I think it will be published, but we're having a little bit of a battle with referees over this point. We've simplified the model to such a degree. We're not even considering a spin 8, a J8 now. We're just trying to qualitatively reproduce what we see in the experiments. And what you're going to find is, of course, when we run this simulation, because it is so small, it's not anything like the real system where you would have the central spin coupling to many protons in the environment. it qualitatively, you're going to see in a moment, reproduces what we observe, but in terms of numerics or quantitative agreement, it's way off. And that's not surprising because it's a...
Yeah, but I have a question related to that. So you said you map it down to spin 1, but J8 is just a 17-dimensional Hilbert space, right? 2 times 8 plus 1.
Yeah,
and spin 1 is 3-dimensional. Okay,
yeah.
so but on a computer, 17 and 3 are maybe not so different. So I'm
Not
just
so
curious,
different,
like, is it because you're doing some analytic calculation?
But then when you couple to 7 two-level systems,
okay.
So you've got 2 to the 7 times 3,
right?
Is small, quite a bit smaller than
right.
2 to the 17 times 3 times 2 to the 7.
Right. Oh, okay.
So, and then the other thing is you want to evolve this thing for a very long time because you want to study the quantum dynamics and recapture this eSIM effect. You need to evolve it over a large amount of time. So you're not just doing one calculation, you're doing a time evolution. But it's exact, and it's very it's very simple. And I'm going to show you how you can do a more precise not more precise. I'm going to show you how you can do a more realistic calculation in a moment. It's not by us, but by another group. So I'll show you that in a moment. But you know, we're experimentalists. That's why I assumed that I would you know, raise a few eyebrows amongst the theorists in showing this model. But the great thing is it really does capture. So we're not trying to reproduce.
No, theorists also suffer from the same problem. We don't know how to get it. So we also have to map down our models to something simpler in the case of spin orbit coupling and so on. So, but I was just curious. Okay.
Yeah. So a simple spin Hamiltonian for spin 1, it just has an axial anisotropy, and then this E term, this rhombic distortion generates the clock transition. Then you have this generates the Zeeman effect and shifts the clock transition away from zero magnetic field, which is what we find in the experiments. And then you put in the hyperfine coupling between the central spin and the protons, nuclear Zeeman, and then the nuclear spin-spin couplings. So so the first thing we do just for fun is just consider the coupling between one nuclear spin and the central spin. And it turns out already you get the eSIM, all right? Because as I mentioned before, this eSIM, the oscillation in the coherence of the central spin is nothing other than a coherent dance between the central spin and the nearby proton. Now, in reality, it's doing that dance with many more than one spin, but even with just one proton spin, you generate very strong oscillations, temporal oscillations in the coherence of the central spin. And immediately, just that simple model with one proton and one electron, it produces all of the frequencies that we observe in our experiment. So it produces a frequency at the hyperfine splitting, it produces a frequency centered at the proton Larmor frequency and split by the hyperfine splitting, and it produces a harmonic at the second harmonic as well. And there are various other combination frequencies here as well. So what you're actually looking here is the time evolution of the coherence of the central spin. So you can see it's rich, it has a strong harmonic content, but it never loses coherence. You know, periodically it always comes back to itself. There's no decoherence in this model. So there's really, this is just a coherent coupling between the central spin and the single proton. So that this ridiculously simple model reproduces the eSIM. And it even reproduces the fact that the eSIM vanishes at the clock transition. So if you look at this splitting here, or this strength of this hyperfine coupling constant, and you plot it as a function of the detuning from the clock transition, it goes rigorously to 0 at the clock transition. So the eSIM does, so you just get a flat line here if you do the simulation right at the clock transition. So you only see the coupling when you go away from the clock transition, where you have a finite expectation value of SC for the central spin. But there's no decoherence. But when you add all 7 spins, now you see much more impressive dynamics. Now, it doesn't really look like the experiment, of course, because it's not the same model. But not only do you reproduce the temporal oscillations with rich inharmonic content, you also produce the decay and the coherence over time as well. So you produce decoherence. So, you know, what you see from this right away is that you need more than one surrounding proton to generate coherence. And in fact, I'll show you in a moment, it requires only 2. So all you need is 2 surrounding protons to undergo a flip-flop process, and you permanently dephase the central electron spin. Of course, they could flip back, and then you get back the coherence of the central spin. But as soon as you start to add more and more electron spins, sorry, nuclear spins, the likelihood that the central spin comes back to where it was at the beginning, it becomes, probabilistically less and less likely. So the decoherence within the context of this model is you just have some deterministic coherent dynamics associated with your electron spin and the surrounding protons. But that results in the coherence of the central spin decaying away over time. And at short times, you see these beautiful oscillations that are due to coherences that develop between the central spin and the surrounding protons. But over time, the coherence goes away and doesn't come back. In theory, one ought to be able to reverse this. I don't quite know how, but in theory, one ought to be able to reverse this process. So this is what you observe. Now, the only thing is the time scale of the decoherence is much, much longer than it is in our real system. In our real system, the decay time was of order few microseconds, and here it's hundreds of microseconds. And the reason for we're off in the order of magnitude of the decoherence is simply because our system is too small. We need to include many more protons to get the time scale right. And of course, we also predict that the coherence, there is no decoherence whatsoever at the clock transition. So all of the oscillations are gone, and there's no decay in coherence at the clock transition. This is just a flat line. Now, in the experiment, of course, we still see decoherence because it's limited by other factors like spin lattice relaxation. Yeah, are you gonna?
Yeah, I have a question. So these simulations you said were for this 8-spin model coupled to this big angular. But do you have some understanding? And you said that the time scale does not match with the experiment, but and you also showed us systematically you did the 1-spin coupled to this other one where there is of course no decay. But if you tried like 3, 4, 5, then 8, 9, 10, like do you have some pattern for how this time scale is changing with number of spins that are coupled? Or
yeah, I have some other simulations that are not mine that I can show you this, and I'll probably end at that point because that was the point that I wanted to get to in the talk, which I could probably do in the next 10 minutes and maybe summarize the last bit really quickly. When I say the time scale, by the way, the coherent dynamics time scales are absolutely spot on. So the
yes, I agree. Yeah. But this overall envelope that
but the overall envelope is off because we're not leaking enough quantum information to enough protons.
Correct.
So the system is not the central spin is not losing coherence fast enough. So basically, this time will become shorter as you add more and more protons, but eventually it will converge to some intrinsic coherence time as you make the proton bath larger and larger and larger. Beyond certain size of the proton bath, it doesn't matter any longer.
Right, because you're saying these couplings are dipolar or something. So it's like there's some decay there.
They're dipolar, so they decay, and below some coupling strength, they just don't matter anymore. But the point is, if you take the Fourier transforms of these time traces, which you can evolve to very, very, very long times, so I'm just showing a snippet here for the first few hundred microseconds, but we can evolve them to extremely long times and take Fourier transforms, and we get rather fuzzy spectra because we have such a small number of spins. There are many, many possible frequencies, but not infinite, associated with the dynamics. So we're sort of looking at a histogram here of all of the frequencies that are associated with this chaotic coupled system of a single electron spin and the surrounding protons. But if you look at that histogram, it really is peaked in the regions where we see peaks in our experiment, which of course there you're considering an infinite system rather than just a single central spin and 7 protons. And we see exactly the behavior we see if we look at the peaks in these histograms. They follow the proton Larmor frequency and the second harmonic, and there's a splitting about the proton Larmor frequency, which corresponds to the effective hypofine coupling between the nearest spins and the central spin, and that goes away completely at the clock transition. So this toy model, even though it might raise a few eyebrows, it really captures most of what we wanted to prove, which is that we can show that this E-seam effect vanishes, so we completely decouple the electron spin from the protons when at these clock transitions. So obviously that's really powerful in terms of a way to enhance coherence in spin systems, and that's one of the reasons why you might consider this type of transition for this kind of spin system as a qubit in any future technology. Now, the last thing I think I'll be able to show, because of the time, I don't want to go over my hour and a half. There was one last segment, but this is the point I definitely wanted to get to. And this is not my work. This is actually a work of another well-known EPR person, Stefan Stoll, who's at the University of Washington, where he's doing more realistic simulations using generalized cluster correlation expansion method. So he adopts exactly the same Hamiltonian that we have. Well, and let me take a step back. He's considering just simple spin 1/2s. So he does experiments on organic radicals. So they're just organic molecules that have an unpaired electron sitting somewhere on the molecules, just a spin 1/2. There's no clock transition in this study. It's just purely looking at the dynamics of a single spin 1/2. And what he does is he freezes these in a very dilute way into a glycerol water matrix. And then he does experiments to measure the decoherence, and he sees eSIM just like we do. And then he tries to simulate the behavior. And the important thing to show here is that the time scale for the experiments and the simulations, they agree really well. They're slightly off on the exact shape of the decay curve. There's a little bit of a deviation from stretched exponential, but they capture the eSIM effect and they capture the coherence time more or less on the money. So the idea here is, and so it gets back to this point that I was trying to make, is that in this method, basically what you're recognizing is that the decoherence of the central spin due to the surrounding bath, there's a sort of assumption that it can be factorized into contributions from clusters. And so what you do in this method, so in his calculations, he considers something like nearly 1,500 protons coupled to a single electron spin. And you can imagine the Hilbert spaces for that is just stupidly large. But the way you get around that is you consider clusters of either 1 proton, 2 protons, 3 protons, 4 protons, and so on. And you can calculate the coherence just by, since the assumption is you can factorize the contributions, you can really calculate the overall coherence just as a product of all of the individual contributions to the decoherence that come from these clusters. And so really all you're doing is you're just doing simple calculations, for example, of 2 protons dephasing the central spin. And then you do that over all possible pairs. And then you calculate the coherence through a product, and you do it with clusters of 3 and 4 and so on. And the remarkable thing that he found is that obviously if you look at single protons coupling to the central spin, because every individual proton cannot by itself cause decoherence, there is no decoherence, even if you consider all of the contributions out to some finite radius. But as soon as you start to consider pairs, now you get the decoherence. And the remarkable thing is that if you do a cluster correlation expansion up to level 2, so up to where you only consider pairs, and then you do it again for up to level 3 where you consider groups of 3 protons, it's already converged. So what it's telling you is that really the main source of decoherence in these systems is just these pairwise spin flips between protons, and you pretty much get the entire decoherence right by considering the spectral diffusion that occurs through the spin flips of 2 protons and how that ultimately bears on the coherence of the central electron spin. So he can produce these curves here just by using a cluster correlation expansion only up to pairs of hydrogen atoms out to a radius of about 17 angstrom. Beyond 17 angstrom doesn't make really any difference to the behavior. And it's even though there's obviously an approximation in the sense that you're doing this cluster correlation expansion and not doing the calculation exactly, in some sense it's still an exact calculation, because he starts out with DFT to predict the structures of the radical and the solvent, and then he does molecular dynamics to figure out exactly where all the protons freeze. So he knows, so he's using first principles to predict the locations of all of the protons, and then he pairwise calculates the contribution to the decoherence of the central spin through this method. And So the sort of the lesson that comes out of this is that decoherence from the spin bath is somehow kind of completely deterministic, as we saw in our experiment, you know, in our simple model. I mean, obviously with 1400 spins, it's a daunting thing, but it really is just an enclosed electron nuclear system. And you're just evolving, looking at the deterministic evolution of the coherence of that central spin coupled to those 1400 or so nuclear spins. And that leads to a decay in the coherence of the central spin. Now, of course, eventually T1 processes will kick in so that you have truly non-deterministic or stochastic loss of quantum phase. And so the system ultimately can't come back. But most of the behavior, the profile over which the coherence decays away is governed almost entirely by this deterministic coupling between the central spin and the surrounding nuclear bath. There's other kind of neat things that come out of these calculations as well. You find that actually its protons are a little bit further away that have the strongest contribution to the decoherence. The ones that are really close in, it turns out they're so strongly affected by the dipolar field of the central electron spin that they get stuck. They find it hard to undergo these flip-flop processes, so they kind of get frozen out of the dynamics. They still can cause E-seam, but they don't cause they don't undergo flip-flops with nearby protons. So the flip-flop processes start to occur further away. So it suggests again strategies for how you might be able to reduce decoherence in these systems. So I'm right at an hour 30. I was stupidly looking at a stopwatch and not the time. I'm probably a little bit over 1:30. So I'm just going to skip to my conclusions. The part of the talk that I was going to skip was simply a different system that we've studied where the clock transition is not due to a crystal field, but it's actually due to a hyperfine interaction. And the lesson there is that, the crystal field clock transition, because it's driven by a crystal field interaction, it means that the clock transition itself is strongly coupled to the surrounding lattice. And so T1 contributions to the relaxation are quite strong when the clock transition is generated by a crystal field interaction. But if you can find some other interaction that can generate that clock transition that's not well coupled to the lattice, like a hyperfine interaction, now you have much longer T1. And so that's work that we're sort of in the process of getting published right now, where we have another lanthanide system with a really strong hyperfine interaction. And that's much more similar to the approach that's being followed in the ion trap community, where typically the clock transitions that they use involve hyperfine splittings. But you have to be very, again, the chemistry there on how you generate a strong hyperfine interaction is not trivial, but we sort of know how to do it. And it's kind of a heroic effort that led to that, but unfortunately I don't have time to talk about it here. So I'll just end here with thanking all of my collaborators, and of course the students at FSU that did a lot of this work.
Okay, thank you very much, Steve. So we have had quite a few questions along the way, but since this is the last presentation, we can take some more questions from the audience if there are any. Yeah, so Steve, maybe I can ask one question slash comment if you wish. So I was a bit surprised when you showed the result that when you have a single proton, there is no decoherence at all. Is that because of some special symmetry of the Hamiltonian for that case? And the same question applies to the case where you have this exact clock transition where the
well, I suppose it's the same reason that where if you have two bodies, they undergo, it's this problem with 2 and 3 body dynamics, right?
Yeah.
You get a very periodic dynamics with 2 bodies, and the same thing is happening with 2 spins. You get a very, in both cases it's deterministic, but you get a non-chaotic behavior when you have just 2 spins. And I think it becomes more and more chaotic as you add I don't know if
So sounds like what you're saying is that energy levels or energy gaps are commensurate in one case, but incommensurate in the other case. In the commensurate case, then the motion, the quantum mechanical motion, purely periodic.
Yeah.
But it becomes aperiodic in the other case.
Yeah.
I see. Okay.
Because
it's sum of periodic functions, but the periods are different, so they can, right? I mean.
Yeah, but I was just wondering
So
because
I think in the thermodynamic limit you can have, that's what thermal I associate with decoherence, right? You have
I mean, I'm
sum of-
assuming that if we picked a central spin and two spins that were resonant, we would probably get a different behavior. So this part of, you know, we positioned the seven spins in a way that we gave them a distribution of couplings to central spin, which is the case in the real system, by the way. So I think for 2 or 3 or 4 spins, you could probably construct situations where it would become periodic. But as you get to larger and larger number of spins,
now, there is actually a more basic difference between one proton and two protons. So for the one proton, if you treat it as a bass, the bass only has a two-dimensional Hilbert space. So the Hilbert space of the bass is actually smaller than your system. Your system is a spin 1 object, right?
Yeah.
So a smaller bass cannot completely decohere the system. So there's always some quantum information that cannot be leaked into the environment. But as soon as you have 2 protons, then your environment has a bigger Hilbert space than your system. Then it becomes possible to completely decohere your system.
that would be interesting.
I was just surprised why it didn't have any decoherence at all for the one proton case. I was expecting that it would decay somewhat, but it will not decay all the way to 0 because it has a smaller Hilbert space.
That's interesting. We haven't checked that. So those are kind of things that, you know, this is a fun toy model. There's a lot of things that we can check with it we haven't checked yet. So that I think of it more the way that I think about it classically, unfortunately, which is probably not the right thing to do. But yeah, I know that as soon as you have 2 spins, you can, yeah.
I mean, one sort of a quick check is that if you increase the size of your system, you find that 2 protons may not be enough anymore. That's one thing that can be easily checked.
Yeah.